Hello guys, welcome to my YouTube channel. We are still on the course STA 221, Design and Analysis of Experiments, and the topic we are still considering is Completely Randomized Designs. Today we'll be doing the partitioning sum of squares. We are going to be partitioning the sum of squares, and the sum of squares, as we've learned in our last videos, is SSE, that is the error term that was squared and that was summed. So this is the CRD model that we've been using so far. So the CRD model is Yij equals to mu plus tau I plus Eij, where mu stands for the overall mean and tau I stands for the ith treatment effect, and Eij is the random error squared. So this is from I to k, 1 to k, I is from 1 to k, j is from 1 to n. I is from 1 to k, j is from 1 to n. So the next step, now we need to know that this is what we abbreviated the same way we did in our last videos as SSE, where summation Eij squared, I equals 1 to k, j equals 1 to n is sum of squared error. So it is this sum of squared error that we are going to partition into the treatment sum of square and the total sum of square. So what we are trying to do now is to show that SSE is equals to TSS minus TRSS. This TSS stands for the total sum of square, and this TRSS stands for the treatment sum of squares. So the next step is to pick this SSE, this equation, and then we begin the partitioning process. So SSE, which is the sum of squared error, is equals to summation Yij minus mu minus tau I. I is from 1 to k, j is from 1 to n. So we then we evaluate this square. So we have SSE equals to summation Yij minus mu minus tau I into brackets Yij minus mu minus tau I. So the next step, I is from 1 to k, j is from 1 to n. So the next step is to open this bracket, and we use each term inside the first bracket to multiply this entire bracket. So we have summation I from 1 to k, j from 1 to n of Yij into brackets Yij minus mu minus tau I minus mu into brackets Yij minus mu minus tau I minus tau I into brackets Yij minus mu minus tau I. So from this point, the next step is to use this summation to open the brackets, this big bracket. So if we do that, we have our SSE equals to summation I is from 1 to k, j is from 1 to n of Yij into brackets Yij minus mu minus tau I, close brackets. Then we use this to multiply for this expression too. So we have minus mu is constant, so we have minus mu this mu cap is constant to these two summation. So if we use this summation to open this bracket to multiply this expression, what we are going to have is mu cap summation Yij minus mu cap minus tau I cap. So from here we have I equals 1 to k, j equals 1 to n. And for this one, we use this summation to multiply these two, and we're going to be using summation I from 1 to k to multiply tau I, and we distribute summation j from 1 to n to the remaining expression inside the brackets. So we are going to have minus summation I equals 1 to k of tau I, then summation j equals 1 to n of the remaining expression in the bracket. So we have Yij minus mu cap minus tau I cap, close the brackets. So having this equation, if we evaluate this particular expression here, it's going to give us 0. And if we evaluate this particular expression here, it's going to give us 0. So let's take a look into that. Let's start with this expression. So that expression is mu cap summation Yij minus mu cap minus tau I cap. This summation, this I is from 1 to k, here j is from 1 to n. So if we open this bracket with the summation, we are going to have mu into brackets summation Yij, I equals 1 to k, j equals 1 to n minus kn mu minus n is constant to tau I, j is constant to tau I, so we cannot sum tau I over j. We sum it over I, which yields 0. So we are going to have n summation I equals 1 to k of tau I. So this gives us mu cap into brackets summation yij, I equals 1 to k, j equals 1 to n, minus kn. If you recall from the last videos we made, the formula for this mu is also summation yij all over kn. I equals 1 to k, j is 1 to n. So, and this summation tau I over I is equals to 0 based on the assumptions of the CRD model. So we have minus n into bracket 0. So from there we have mu cap into brackets summation yij minus, now this kn cancels this kn, so we have summation yij minus 0, close brackets. Summation yij minus itself is going to give us 0. So eventually we have this into bracket 0 and it gives us 0. So that is why at this point the evaluation of this expression is 0. So it cancels out. Now the same for this last expression, we have to evaluate it, which will also give us 0. So if we evaluate this last expression, let's go through that. So that expression is summation tau I equals 1 to k, summation j equals 1 to n into bracket yij minus mu cap minus tau I cap, close brackets. Now based on the assumptions of the CRD, summation of tau I over I is equals to 0. So therefore this entire expression here becomes 0 multiplied by summation of yij minus mu cap minus tau I cap, which will give us 0. And that is why this expression at this point was also evaluated to be 0. So now our SSE then becomes, we are left with the first expression alone, and the first expression is this. So our SSE is going to be summation yij into brackets yij minus mu cap minus tau I cap. Since this and this have already been evaluated to 0, so we have SSE equals to summation I equals 1 to k, j equals 1 to n, yij into brackets yij minus mu cap minus tau I, close brackets. Since this is what we are left with for our sum of squared error, so the next step now is to open this bracket with summation yij, and so our SSE is going to become summation yij multiplied by yij, now yij squared. So I is 1 to k and j is 1 to n minus, so we then use summation yij to multiply mu cap, and that gives us, since mu is constant to I and j, we have mu cap summation yij. So we have I equals 1 to k, j equals 1 to n. Then we sum tau I over I equals 1 to k. So we have minus summation I equals 1 to k of tau I. Then summation, to remain this alone, we have yij, I equals 1 to, j equals 1 to n rather. So j equals 1 to n. So the next step is to break this down. So we have SSE equals summation yij squared, I equals 1 to k, j equals 1 to n minus, so if you recall from our last videos, the formula for this mean, the equation of the overall mean, is also summation yij, I equals 1 to k, j equals 1 to n all over kn. And so we multiply by this expression beside it. So we have into bracket summation yij, I equals 1 to k, j equals 1 to n, close brackets, minus then this. So we break tau I down into its original equation. So we have summation I equals 1 to k. Then the equation for tau I, which is the derivation of the treatment mean effect from the overall mean effect, is going to be yi dot, and yi dot can be written as summation of yij, j equals 1 to n all over n, minus y dot dot over kn, and y dot dot over kn is the same thing as our grand mean, which is summation yij, I equals 1 to k, j equals 1 to n all over kn. All these parameters have already been estimated in our last videos, so multiplied by this last expression beside it, summation yij, j equals 1 to n. So from here, if we multiply these two expressions together, we are going to have summation yij squared. So we have SSE equals to summation yij squared, I equals 1 to k, j equals 1 to n minus summation Yij all squared. I is 1 to k, j is 1 to n over kn. Then for this last expression, so we can use this two summation to open the brackets. And if we use this to open these brackets, this is going to give us minus summation I equals 1 to k of summation Yij over n, j equals 1 to n into bracket summation Yij, j equals 1 to n, close brackets, minus, if we combine this term outside the brackets and this one, that's going to be summation Yij. And if we multiply it with this, it's going to give something like this, summation Yij squared. So we have summation Yij over kn, I equals 1 to k, j equals 1 to n, into bracket summation Yij. So from there, our SSE then becomes summation Yij squared, I equals 1 to k, j equals 1 to n, minus, and this summation Yij can also be written as y dot dot. That has already been explained in our last video. So we have y dot dot squared over kn. This is going to be y dot dot squared all over kn, since there are two summations here, and both summation are over I and over j, and this is also Yij. So each sum represents a dot. So that's that. And for the last expression now, this summation over j of Yij is what we usually denote by yi dots. So this is going to give us minus summation of I equals 1 to k of yi dot square over n, because this is going to be yi dot and this is also going to be yi dot. So if we multiply them together, we're going to have yi dot square over n. So we have yi dot square over n, then minus. So if we multiply this together, this one is also y dot dot, this one is also y dot dot. So if we multiply these two together, we get something like this. So we have y dot dot square over kn, and this is our partitioned sum of squares. So where this expression here on the left hand side of the minus sign represents our total sum of squares. J equals 1 to n, and also our treatment sum of squares is going to be this expression on the right hand side of the minus sign. So we have summation I equals 1 to k of yi dot squared all over n minus y dot dot squared all over kn. And so our sum of squared error has been partitioned into TSS, which is total sum of squares, minus TRSS, which is treatment sum of squares. Thank you.